let us discuss about adjacency matrix of a graph. We can represent a graph by a matrix. Here we are going to discuss how to find the adjacency matrix of a given graph. So here we consider a graph with n vertices. Consider a graph with n vertices and no parallel edges. The corresponding adjacency matrix is a symmetric matrix of order n by n. So here if there are n vertices, the corresponding adjacency matrix will be a symmetric matrix of order n by n. And here the adjacency matrix is denoted by capital X and is equal to matrix Xij, and it is defined as follows. Xij takes only two values, 1 and 0, and here it is 1 if there is an edge between Vi and Vj, and equal to 0 if there is no edge between Vi and Vj. If there is no edge between Vi and Vj. So here the adjacency matrix takes only two values, 0 and 1. So here we can say it is also a 0, 1 matrix. Now let us move to one example. So here we can consider a graph . Let us consider this example. Now we can name its vertices like this. This is V1. Then here we have V2, V3, V4, V5, V6. Now we can name the edges also. Here we can name it as E1, then here E2, E3, E4, then E5, E6, E7, E8. Okay, now the corresponding adjacency matrix is given by X is equal to, here we can see that there are 6 vertices. Here n is equal to 6 and the number of edges E is equal to 8. We already see that the corresponding adjacency matrix will be a symmetric matrix of order n by n. So here we have a symmetric matrix of order 6 by 6. Now we can arrange the vertices here V1, V2, V3, V4, V5, V6. Similarly here V1, V2, V3, V4, V5 and V6. Okay. Now first we consider the vertex V1. Now there is no self loop. Okay. So V1 to V1 there is no directed edge. There is no edge. So we can write the entry as a 0. Okay. Similarly, Here from V1 to V2 there is an edge E1. So here we can write it from V1 to V2 we have a 1. Okay. Similarly from V2 to V1 also there is 1 because here there is no direction. This is a undirected graph. Okay. So here next we have from V1 to V5. V1 to V5. V1 to V5. Here we can write 1. And also V5 to V1. V5 to V1 also 1. Then V1 to V6. From V1 to V6 1. V6 to V1. V6 to V1 is 1. Okay. So next we can consider the vertex V2. Now V2 to V2 there is no edge. Now V2 to V1 we already considered. Now V2 to V4 there is an edge, so put it as 1. Then V2 to V5 there is an edge, so write it as 1. Okay. Now all other entries are 0. Now let us consider the next vertex V3. Now V3 to V4, V3 to V4, V3 to V4 there is an edge. Similarly V4 to V3 also there is one edge. Okay. Then next we have a V4 to V2. V4 to V2 already one is there, and from V4 to V5, V4 to V5 there is an edge. Then V4 to V6 there is an edge. Okay, so this is our corresponding entries. Next we have a V5. Now V5 to V1 is there. V5 to V2. V5 to V2 is one edge. And from V5 to V4 there is an edge. And all other entries are zeros. Okay. Next we can consider V6. Now V6 to V1 there is an edge. And V6 to V4 there is an edge. And all other entries are 0. Similarly, we can put zeros in the other vacant positions. Here we have 0, 0. And in the next we have 0, 0. Here also 0, 0, 0. Then here 0, 0. Then here we have a 0. Then V4 to V2 there is an edge. So here we have 1. Then V4 to V4 no. So 0. So this is our required adjacency matrix. So here the entry is Xij takes the value 1 if there is an edge between Vi and Vj. Okay, if there is an edge the entry is 0. If there is no edge between any two vertices the entry is a 0. So that is the method of finding the adjacency matrix. Now we can move to the observations from this adjacency matrix. Okay. So what are the observations here? So we can consider the observations. So the first observation is the entries along the principal diagonal of X are all zeros if and only if the graph has no self loops. So here we can see that the principal diagonal of X is complete 0. So here why? Because there is no self loop. So that is our first observation. A self loop at ith vertex corresponds to xii equal to 1. Okay, so here we can see that xii equal to 0 in this particular example because there is no self loop, and xii equal to 1 if there is a self loop. That is the first observation. Now second observation, the definition of adjacency matrix makes no provision for parallel edges. This is why the adjacency matrix of X was defined for graphs without parallel edges. Okay, so let us move to the third observation. If the graph has no self loops and no parallel edges, the degree of a vertex equal to the number of ones in the corresponding row or column of X. Okay, so here the number of rows in the number of ones in the first row is 3 and number of ones in the first column is also 3. Why? Because the degree of vertex V1 is 3. Okay, so depending upon the number of edges joining to a particular vertex, that means depending upon the degree of a vertex, there will be that much number of ones in a particular row or column. Okay, that is our third observation. Now, the fourth observation is permutations of rows and of the corresponding columns imply reordering the vertices. The rows and columns must be arranged in the same order. Thus, if two rows are interchanged in X, the corresponding columns must also be interchanged. Hence, two graphs G1 and G2 with no parallel edges are isomorphic if and only if their adjacency matrices X of G1 and X of G2 are related by the relation X of G2 equal to R inverse dot X of G1 dot R, where R, capital R, is the permutation matrix. Now, the fifth observation is a graph G is disconnected and is in two components G1 and G2 if and only if its adjacency matrix X of G can be partitioned as X of G is equal to X of G1 0 0 X of G2. Here X of G1 represent the adjacency matrix of the component G1 and X of G2 represents the adjacency matrix of the component G2 and 0 represent 0 matrix. This partitioning implies there exists no edge joining any vertex in G1 to any vertex in G2. Next we have the sixth observation is given any square symmetric binary matrix Q of order n, one can always construct a graph G of n vertices and no parallel edges such that Q is the adjacency matrix of the graph G. Okay. Now, let us consider one theorem now. The statement is like this. Let capital X be the adjacency matrix of a symbol graph G. Then the ijth entry in X raised to R is the number of different edge sequences of R edges between vertices Vi and Vj. Here we can prove this theorem by using induction on R. Okay. Now we can consider a corollary. In a connected graph, the distance between two vertices, the distance between two vertices Vi and Vj, here you consider I not equal to j, that means Vi and Vj are different, is k if and only if k is the smallest integer for which the ijth entry in x raised to k is non-zero. Okay. Now we have another result. Now we can consider it as B. If x is the adjacency matrix of a graph G with n vertices and y equal to x plus x square plus etc. plus x raised to n minus 1 in the ring of integers, then G is disconnected. G is disconnected if and only if there exists at least one entry in the matrix Y that is 0. Okay. So in order to prove a given matrix is connected, it is enough to calculate y equal to x plus x square plus etc. plus x raised to n minus 1, where n is the number of vertices, and prove that all entries in y are non-zeros. Okay, so this is the method of proving a given graph is connected. So this is one application of the adjacency matrix. So in order to prove a given graph is connected, we can make use of the adjacency matrix. We can just consider the number of vertices and then find x plus x square plus etc. plus x raised to n minus 1, and you look over all the entries. If all the entries are non-zeros, you can conclude the given graph is connected. Okay. Thank you all.